Hello everybody. So this is the very first live coding Twitch stream on the GRiSP channel. So I hope anybody's watching actually. And this works. So does anybody see anything? Yay, I get some messages here. Good. So today the plan is to first bore you with a short slideshow about like what GRiSP is about, since this is the first video on the stream and people who might not know about how GRiSP works might drop in and need a short introduction, and then I will lead over to where GRiSP will be going and basically show you the next version of the hardware or talk about it. And at any time, please feel free to ask any questions in the chat window, and I will just interrupt and answer them. After that, I will start my little Twitch project, which I'm planning since a while. So today we will probably only do some live coding, how to get started with a project. Later on, this should migrate into controlling my home solar heating system, which is not controlled yet. More about that later. And that will be the episodes I will actually showing while I'm developing the actual system. So I hope everything works today. Let me switch over to slideshow mode and pop up Keynote. So unfortunately I can't see anything anymore because this only works in full screen, but I really hope it works for you. Let me shortly check on the iPad if it's actually working. Oh, that's still offline. Perfect. I see it here. Oh, now I'm getting the advertisements on the iPad. That's not good. So, short introduction. Yeah, that's what we do. We make embedded systems and use Erlang for embedded systems. So all these things that you see here are embedded systems. I've talked about this like quite often, so I don't bore you with it. So this is like kind of the predecessor to the GRiSP system. These little boards here control this conveyor belt system for Bosch Rexroth, and they run a predecessor to the current GRiSP software stack on different hardware. And we use a network of 15 of these boards to control demonstrate a conveyor belt system with 8-meter lengths. So we probably wouldn't need that many boards, but it is about like showing that we can do distributed control systems. And there's also a video. I hope this works well. So that's how conveyor belt system like this then looks, that these pellets move around along the conveyor belts. They get fixed. And there's like ways to go in multiple ways, which need to be controlled. And there's another corner here. And we also have an RFID system, also written in Erlang. And this movement is also, so everything that moves here is controlled by these Erlang nodes, basically. So a few examples what we do with GRiSP in the real world. We made a prototype for a remote sensor assessment technology for trails. To actually measure the tilt and all kinds of things, and we were able to make a prototype pretty quickly to show that it's actually working. And this is probably this year heading in towards the production area. We also use the GRiSP board together with QuickCheck to run hardware in the loop tests driven by QuickCheck, where we control this machine that lifts cases off the floor so you don't have to go down. And we test this machine. So the actual machine stands behind the screen, and I can't show it at the moment. And we move it basically. We use the GRiSP board as an interface between the testing setup and the actual hardware. That's quite old. That's kind of like our first GRiSP project, a little robot with an ultrasonic sensor that moves around and tries to escape or follows you or whatever. So that's just a little toy thing. That was a pretty quick project. GRiSP is also used in research. Igor Kopesensky is using it in the Litecoin project to do clusters of GRiSP projects. And actually, we have him here today in the chat. So probably it's the only one that wrote something yet. Apparently that's also very useful, but I don't want to go into details here because we want to get to the live coding. So we also have an internal research project that basically initially a master thesis was done on this to actually support hard real-time processes on the Erlang or Elixir level, which is possible because the whole thing runs on a hard real-time operating system, which is the minimum requirement to actually run hard real-time things on higher levels also. So short introduction what the board is. So this is about GRiSP-1. This is about the board we are playing with today. It has a CPU. It is a medium-sized CPU. So this CPU wouldn't run Linux well. It's too small, not memory-wise, but it doesn't have a decent virtual memory implementation. We use a SD card for storage, and we have 64 megabyte SD-RAM, which is plenty for Erlang. I mean, it depends on the application, of course. We also have our Wi-Fi on board for networking. And we can also switch off the Wi-Fi because Wi-Fi takes a lot of power. So in GRiSP-1, Wi-Fi is the only networking thing. There's one wire and I2C. I don't want to go into much detail here because probably along my little project we will learn one thing or another about one wire and I2C. There's these black connectors on the border. That's where you can connect PMODs, and there's different kinds of PMODs and different kinds of interfaces, which are the usual interfaces that are existing on CPUs. So that's how PMODs look. Here in the picture, we have a GPS, a motor controller. I think another motor controller in the back, a little bit blurry, and like navigational PMODs, like accelerometer meters. 10 degrees of freedom navigational sensor. So you can get like 1 to 200 different PMODs on the market. The interface is standardized, and you can get all kinds of sensors, radios, motor controllers, and other actuators. So GRiSP is actually a software stack, and the actual thing that makes it tick is that we use the standard Erlang VM. And we embed it with Atoms, which is not an operating system per se. It's more like a unikernel, as we would call it nowadays. So what happens is that the Erlang VM and the Atoms library gets linked together, and this gets booted on the hardware. So there's no kernel mode, and basically everything is running on the hardware, but more on this. And this combination we call GRiSP. That's the actual software stack. And the board is just a way to get started quickly and have more fun with it. So short comparison of architectures. So traditional architecture, we have hardware on the lowest level. I think you can see my mouse. There's the hardware, and on top of the hardware is the operating system, and on top of the operating system in user land, there's the Erlang VM running the Erlang application, and there can be other software here. But to access the hardware, it also always has to go through the operating system into kernel mode and to get at the hardware. In GRiSP, what we have a different approach. Basically, the Erlang VM and Atoms and possibly other libraries are linked together, and the Erlang application is running in this like unified Erlang VM. And this Erlang VM linked together with Artemis is booted directly on the hardware. So if we want to access the hardware from any level, this is direct. There's no kernel in between. There's no intermediate steps, which gives us less latency. Actually, I'm just noticing that I can't answer questions during the talk because I don't see your chat. So I will answer all the questions. Just keep on chatting and I will answer the questions afterwards. The GRiSP runtime provides the low-level protocol drivers for all these PMOD and connectors. So that's already built in. And we also have the higher level drivers like on the Erlang level, which lets you access the low-level interfaces, or we have ready-made drivers for common PMODs. So that's how a driver would look like. The usual thing, you have an application, you have the Erlang driver, you have the SPI API, which basically calls into a C driver, which can also be a NIF. In this case, it's a C driver because when we were starting with GRiSP, we were not able to use NIFs because NIFs depended on being dynamically loaded, and we can't load anything dynamically. Everything needs to be linked statically. Nowadays, it's possible to link NIFs statically, so we probably will migrate everything to NIFs also, like the OTP team does with all the I/O stuff. And the SPI driver can then use the board support package, which is a library, a board-dependent library, sub-library basically of Artemis, which sometimes has some abstraction libraries to access the hardware. A lot of things is hidden in the tooling. We started with a rebar plugin where all the tooling is done. I will talk about during the thing what's actually happening, so I don't bore you with this. Just wanted to say that we factored out all the hard stuff and the complex stuff into a library, GRiSP tools, and there is two thin layers, basically rebar GRiSP and mix GRiSP. So we have seamless tooling for Erlang and Elixir nowadays. A short word on GRiSP 2.0, which is not there yet. We are basically on the way making it, and we are running a Kickstarter to support this. So GRiSP 2 is basically an evolutionary change on GRiSP 1. We evolved the hardware, we fixed things that we didn't like, and we add features mainly. So GRiSP has an IMX6 CPU, which is a little bit larger than the Atmel SEM CPU. Both are ARM CPUs, but the Atmel is a M7 and the Cortex and the IMX6 is a Cortex A7, which means that the IMX is a little bit larger and would also run Linux. You don't need Linux, and we don't for our GRiSP software stack we don't use Linux, but it would be large enough to run Linux. It's also slightly faster and more megahertz, and we have more memory on. But at the same time, it's not. We use a very ultra low power version of this IMX6 CPU, so it's not actually taking more power than the GRiSP 1. Rather less actually, because we are avoiding a few pitfalls which cause higher power consumption on GRiSP 1. But when I say higher, it's not really higher. It's this is like all of these boards use, for example, much less than a Raspberry Pi. Also, a difference is GRiSP 1 is a fixed design, as you will see soon, and GRiSP 2 will be a modular design. So we have a system on module on this, which allows it an easier step to actually own hardware designs, because all the crucial and all the hard to design parts are on these system on modules. And these system on modules basically are a CPU that runs Erlang. And we have an additional storage option. We also have eMMC storage, which is soldered on, which is the same as an SD card from the protocol, but it's soldered on, so you can't fall out of a plug. But in addition, what is not visible in this table, we also provide a SD card slot. So we have eMMC or SD card to boot. Or you can boot from eMMC and have your application there and store data on the SD card, for example, without fearing to overwrite your application. So that's a rough sketch how it will look. The green thing here in the middle, that's the system on module. Otherwise, it looks pretty similar than the other board. One thing we fixed because of the Ethernet connector, that's one difference. We also provide not only Wi-Fi, the Wi-Fi is still back here. We also provide Ethernet in addition, so you have more choices here. And because of the Ethernet connector, we have to make the board a little bit longer, which allows to have all the PMOD connectors in one row, which is much nicer because this one connector over the corner kind of like, if you plug the PMOD in, it stuck out like in a weird way and prevented, or actually required a much larger case if you want to put it in a case. Goals, new faster modular hardware. We're also cooperating with the NERVS projects. NERVS is another way to actually run embedded, in this case, Elixir applications. But I think they also support Erlang now, or they always support Erlang, but basically it's written in Elixir. The base thing is written in Elixir, and you can use it with Erlang and Elixir. The difference between NERVS and GRiSP is that we boot the Erlang VM directly on the hardware, and we have hard real-time. And the NERVS project uses an embedded Linux operating system and boots the Erlang VM as process 1, which gives you full control over what runs on your hardware and gives you much better real-timeness than a normal Linux system. But it's a different approach, and since we support both with the new hardware, we support both projects, and the NERVS project will support the GRiSP board and make it run on the new GRiSP board. You have more choices, so you can actually, depending on the application, you can pick the right operating system choice here. We also will support the firmware update infrastructure that the NERVS project built, because it's very nice, and we don't want to reinvent the wheel here. So we will support this also for GRiSP. And we also have a special crypto chip on, which the NERVS project already has a driver for. We will also provide a driver for, where you can safely store certificates. This was a request from the NERVS project, and we are happy to actually put it on. And we have Ethernet and Wi-Fi. And that's about it. And you can support us backers on Kickstarter, blah, blah, blah. The link is also on the Twitch page. We already fully funded, but we have a few nice stretch goals we didn't reach yet. We are pretty short before we actually will make a case for like a nice box for the GRiSP board and a few PMODs. And the next level would be that we make a battery controller, which allows you that if you plug the GRiSP board in, it would run from the plugged-in power and charge the battery. And if you unplug the power, it would run from the battery until the battery is empty. And so this is like a built-in battery-powered thing, which also would allow, for example, solar-powered things stuck in a tree, where by day you charge the built-in battery from the solar panel, and by night you discharge it again. So yeah, backers, if you want these stretch goals, or if you want to be the first to get a nice board, and also probably a cheaper board. And that's it. That's actually, I don't think that's kind of like self-referential here, because you're already on the Twitch channel. But if you see the video elsewhere, this is a new Twitch channel. We will be online and streaming every Friday at 18 o'clock and do nice projects around the GRiSP board. So you will see Erlang and Elixir, probably more Erlang and less Elixir, because we are more confident with Erlang live coding, but we might have some guests who do some Elixir live coding, for example. So let me switch to a different screen mode. Okay, so I see the question now is, are any of those projects open source by any chance? Basically the things that we did, kind of like the robot would be open source, but it's actually, there's nothing there yet. I mean, it's really simple. So if anybody wants the code, or you can have it, but it doesn't do much. It's just one hacky little module that actually makes the robot behave. So the other things, the lifter test and the accessibility tool, and is not open source. I suppose your own stuff is open source, Igor, so you probably can answer that. Will your project be open source by any chance? I suppose yes. So yeah, that was the theoretical thing. Let's get to the live coding part. We also want to get some live coding done. So we have 40 more minutes to the full hour. So yeah, Igor just said that his project with a research prototype is everything is open source. I thought so, but I wanted to hear from himself. So today, basically, what we want to do is get started with the project and get something done. Basically, first from zero to Blinkenlight, to show also how easy it is, and then we might get started. I don't know how far we get. Basically, set up a nice development environment for the actual project. So hook up the GRiSP to my Wi-Fi, make remote shell work, and all these things. Let's see how far we get. So that's the plan for today. So solar heating system. So in the house I'm sitting in, there is a nice solar heating system with like with altogether 5,000 liter water tanks and 30 square meter solar heating, which basically warms up water and can also help the heating. The unfortunate thing is that while I'm in the business of making control systems, I need to show you something. All the time, like the last years, the solar heating system was controlled by this. So this were just a bunch of light switches. I hope you can see it. So basically, when the sun came out, I had to switch it on. And if I forgot to switch it on, there is no warm water. And there's multiple switches because there's 2 tanks. And there's also like the wooden stove can actually produce warm water too. And that was my control system. It's a little bit better already by now. It's kind of like already a little bit prepared for a GRiSP board, hardware-wise. I'll probably show you a video next time, or maybe if I manage how to do it, I'll walk you through the house and show you the heating system itself, and where we want to plug this in. It's a little bit better, but it still switches. So I have to switch on I have to flip the switch to actually get warm water. Otherwise, just the water boils, and I don't know. Yeah, it's kind of embarrassing that it's still not control system, but yeah, the stuff we do for customers and for GRiSP boards and all kinds of things keep us busy, or keep me busy because it would be my personal project. And yeah, we have a saying in German that I think the English version is the cobbler's children run bare feet. So basically the shoemaker who makes nice shoes doesn't have time to make shoes for his own children. And that's how my solar heating system works. Let me get to the other setup here. Does this work? Yes, this does work. So I'm sharing part of my screen here, and you also see me in the little corner. Of course, also the chat, if you would chat anything. And there's another camera here on the table where I already placed the GRiSP board. So you can actually see what I'm doing with the GRiSP board, and can follow what I'm doing on the screen. So yeah, as you can see, my favorite editor is Emacs, but this is not dependent on Emacs. And I'm here, I have a terminal window open, and if I list the files, it's empty. So we have an empty directory, and you want to get started with a new project. Maybe first a reference for anybody who wants to do this themselves. There is, if you go on our GitHub and also on our website, so the content is mirrored on our website. If you go to our GitHub organization, then you will find like several repos, which consist of like whatever we do with GRiSP. Oh, actually, I think the robot is the open source robot, so the robot is also open sourced. And there's one repo which is called GRiSP itself, which is the Erlang runtime library for GRiSP. And in this repo, you actually find a wiki. And in this wiki, so here I click on the wiki. In this wiki, you actually find the first steps, and that's kind of what I will be following here to actually set up my development environment. So I move this out of the way so I can actually see my screen. So what I already did is I have Erlang installed. So we have an Erlang installation. In this kind, we have OTP 21.0, I think, still, which is the one I still mainly use with GRiSP, but we have other versions also, and we support all kinds of versions. And as a matter of fact, we're actually building a CI system that we can do matrix builds with OTP versions. So we will support much more versions and combinations of versions of our library, of Artems and of GRiSP in the near future. What I also installed globally, which is only necessary for this first step I'm doing, is our GRiSP Rebar 3 plugin. So I can't show you how it's installed because it's already installed, and it allows me to do things like use templates to create new projects. Because if this wouldn't be, basically you could create a GRiSP project manually or copy something and put the Rebar plugin just as a dependency. That would just work, but then you can't use the templates because for the templates now nothing is there, so you need it globally. So that allows me to do things like to do Rebar 3 new GRiSP app, and now we get to the first problem. How do we name this? That's a good question. Maybe GRiSP home controller, but that's a pretty wide scope. Solar control. That's too long. Maybe attach GSOL control. Oh, well, now it's stuck. And one thing it also wants to know here when you make a new thing is a destination. That's where, when you want to deploy it, where the actual deployment could be. You could put a temporal, we could put a temp here, but we can use the feature to deploy directly to the SD card. That would be, so I would need to put the path here. I'm on a Mac here. So this is like stuff gets mounted on the volumes. And I normally format all my GRiSP SD cards with the name GRiSP. So they get mounted on the volumes GRiSP. And so I can actually rely on that this path will always work. And when we do this, then basically, yeah, it writes a few things and we have a directory now. So we go in there and have a look at it maybe. Maybe just look at it in the editor. Projects, Twitch projects, GSOL control. So that's what we have here. We'll put a license here. Well, Apache is fine, I think. Well, there's a git ignore, a readme, which is empty, and a rebar config. So let's have a look at the rebar config. So this is pretty minimal. It has put in a default dependency here, which is the GRiSP runtime library itself. We switch on debug info. And then there's a section GRiSP, where we kind of like pick the OTP version. I need show parent mode, otherwise I can't live. So there's the OTP version. More on this later, what this makes. And deploy destination is basically the thing that I just entered. And there's for Rebar 3 shell, you can have several apps, but we don't use it at the moment. Here's the relics part where you have to specify your release. So we have one release which is called GSOL control. It has the version 0.1.0. You have to remember that. And basically in the release we have just the GSOL control application. So pretty basic. And at the same time, if we go back to the directory view, it actually created an app source file, the usual thing, and basically the application behavior, which lets us start the application, which just starts the supervisor, and the supervisor has no children. That's it. So let's see if we can build this. Rebar 3 compile. Seems to work fine. So what we now did is we just compiled the Erlang stuff. Move this out of the way. What we want to actually have is to have all the things on the micro SD card, which we then can plug into the GRiSP board. So I put it in this little adapter. The iMac I'm sitting in front of has an SD card slot, so I put it. I don't have a camera at the SD card slot, so I put it in the SD card slot. So there should be a volumes. I pre-formatted the SD card, so that's all the preparation I did, except so there is a volumes GRiSP empty SD card there where we expected. So now we can actually deploy the thing, and then more stuff happens. So Rebar 3 deploy. No, GRiSP deploy. I always have to write GRiSP before to talk to our GRiSP deploy, and the deploy needs you need to actually tell it which release you want to deploy, because in theory, I mean, we only have one release. So if you look at our Rebar config, we only have this one release here. But you could have multiple releases, and now you have to pick which release you actually want to deploy to the SD card. So this needs a name and a version. There's a long version, but I only remember so -n is the name. GSOL control, and the version is 0.1.0. And then it actually should just work. So let's see. I did not try this before. So what we see here, it's basically building some more things, or it basically links the pre-built stuff that we already compiled. And what we see here is downloading pre-built OTP package. So we have these cross-built OTP linked together with items, and since the cross-build thing is not dependent on the host operating system, it's actually easy to provide a downloadable version of this. Actually, I've buried my chat window here. That's not good. Oh, yeah. Okay, Adam says Robot is currently a private airport, but we could open it up, yeah, if really somebody wants it. Where was I? So basically it downloads the pre-built OTP package. So because the cross-build stuff is not dependent on my host operating system, we only need to provide one version for for every OTP version and every Artemis version. So you don't have to build this, because this is kind of like a longish process, because before you could actually build this, you need to pre-build an Artemis toolchain, which takes quite long, because it makes a GCC and linker and all the toolchain, and then it compiles Artemis. So this is even on a fast machine, it takes longer than an hour. But fortunately, quite often you don't have to do this. Basically what happened here is that the Rebar plugin checked if the C source code in all the applications has changed. So it goes through all the applications and collects all the C parts, because you could have C parts in your applications, and we will see this probably in later episodes when we actually have to write some C driver thingies to make my solar pump really run well. It goes through all these source codes and basically creates a magic hash out of it, a unique hash, which would change whenever any of the source code is changed or any source code is added. Because once you change the C parts of these of your dependencies, or add a dependency that has C parts, then it's not, you can't use the pre-built OTP anymore, because everything everything is dependent on the C code and linked together statically. So then you would actually need to make the toolchain. But the good news is that I was talking about CI builds. While we are doing these CI builds, we also will provide eventually pre-built toolchains. So even the toolchain can be downloaded and will be also much more seamless. So I just read that Igor's record is 22 minutes for Artemis toolchain building, which is pretty fast. But here, I think he has an insane setup here. I can't do this on my Mac. So you can see cached file is up to date. Yeah, on this machine, probably this has been done before, because we also cached these downloads. So it does not actually get downloaded. So it has a cache, and if the cache is still the right version, and then it can just use the cache. So everything is up to date, and then verifying dependencies, it compiles the application again, and then it does the relic thing and builds a release. And here, release successfully created, and deploying to volumes GRiSP. So what we would expect now is that in volumes GRiSP there is something. Oops. And alas, there is, or not alas, that's actually good. So let's have a, I just used the Emacs editing thing, because then I don't need an extra window. So there's a file GRiSP ini, and there's a directory gsol control. So the GRiSP ini, if you look at it, that's an ini file which configures a few things. It has a section, it's basically ini file format, which you might know from Windows or from other tools. There's an image path, that's actually the thing that gets booted. And the prefix here, the media MMSCD00, that's the default place where the SD card gets mounted, gets auto-mounted when the whole thing boots. And then we basically look into this directory. That's the directory you saw before, gsol control, which is the name from the release. And we have ERTS 10.0 bin, and this beam.bin, this is actually a raw image of the whole beam. Anything of the Artemis library that's necessary to actually make it run. And this gets loaded into memory, and then the bootloader just jumps there. So there's a bootloader on the GRiSP board, which tries to mount the SD card, reads this file into memory, and jumps to the beginning, basically, or to a predefined position. And from then on, basically, beam.bin takes over. So the bootloader is then out. That's confusing for some, because they think, yeah, the bootloader is still like doing things, but it's not. And then we have a section Erlang which has a single argument here. So it's our command line arguments that that kind of like the fake command line arguments that we get into the Erlang runtime system. One note here: this is not the full arguments. So that's you need to, for one thing, sometimes you need to specify extra things, and not all the features are supported here. So if you normally call error, if I do this on the command line, then the program ERL is run, which massages the command line arguments and sets up an environment, and then basically executes another file, lexec, which then starts the actual runtime system. And since we don't have processes and we can't start other programs, we fake all this and we basically leave away. We only have partially implemented what the ERL program does. So you cannot use all the features on the command line argument, because some of the things, for example, like reading arguments from a file, is done by this like pre-startup thing, which massages the command line arguments in the environment. And then we have a network section where basically IP self, we expect a DHCP server to get us the IP address, and the VLAN is enabled. But probably that doesn't help us yet, because at the moment the GRiSP doesn't know which VLAN to connect and what the password would be. So just to show this and to show the rest, what's on the SD card, there's a directory, and this is basically just a normal Erlang release. We have the bin where we can. No, that's actually boot scripts. That doesn't. That's not the one I wanted to show. This one. So that's where the beam.bin is. So that's the beam with symbols. You see it's pretty large, and that's the actual image that gets loaded into memory. So at the moment, with Wi-Fi driver and everything, TCP stack, FreeBSD compatible TCP stack, we have about 6 megabytes. Not all of 6 megabytes. We could strip this down, but we have 64 megabytes, so this is still plenty. So, and the rest is just, if you look at source, no, not source, sorry. Where am I? Oh, I mean in the runtime system. So actually in lib, you would basically see all the applications that get made together. The GRiSP applications, our own application, the Erlang kernel, standard lib, and a helper library that is necessary by the GRiSP library. So that's the normal thing. But yeah, this is boring. Let's just boot this. Let me just get out of the directory again. And now I have to disk util eject. I could also use Finder, but I use this command line to show that this can be done on the command line, because we can automate this later on. And now I can actually get my SD card and get it into the GRiSP board. So that's, I hope you can see this. So that's the SD card I wrote, and I put it here in the GRiSP board. It's actually getting a little bit dark now, so I have to switch the light on probably soonish. And now it's ready to go. So what I also prepared here, I also provided a USB cable. So I plugged this into the GRiSP board, and over the USB cable, the port gets powered, and you also can watch the console here. And in theory, you can debug. So we get a red light here, and then a blue light, and something blinks. So that's the bootloader still talking. And it loads stuff, and and then it doesn't get green. Oh, it gets green. So this is basically when the Erlang VM starts. At the moment, we still have a problem that we boot too slow. But I actually want to show what happens when you boot. So I mentioned that we have a serial console. Oops. To stop it and start it here. So we are using the serial tool because it's very nice on the Mac. But what would work everywhere is just to use screen. How this is done is actually described in our wiki. But yeah, I mean, serial up gives a nicer experience. So when we open it, it shows us two things, and also shows us a Bluetooth thing that's the built-in Bluetooth in the Mac. And there's two ports here, and actually this tool actually reads from the FTDI how it's named, so it's actually named GRiSP. On other operating system, it's not so nicely named. It's usually called USB serial something or USB TTY and a number. And what we want is the second one, because the first one is for debug, for a JTAG debugger. So we want to open the second one by whatever numbering, and then we get a longish window, which I have to, come on. Why can't I resize this? No, can't resize it. Okay. I think that's in the preferences. So we need to set it up a little bit. So it actually remembered my last setup. So the there it is, settings. Yeah. So in the settings, we want to have 115/200. That's the default baud rate, 8 bits, parity none. So that's standard things. And we have special terminal settings. We use Xterm, but you can also use VT100. Important thing is kind of like the line editing is a little bit broken on the console. So to actually use the shell, it's this provides line buffered, and also we want to locally echo the type characters because you don't get echo. So actually I got a shell here already. So we can actually do things. And we could also do things like GRiSP, LED, set. Oh, I never can remember this. Let me check my. Let me check the documentation quickly. Yeah, let's not use set, let's do flash because it's like more flashy. Flash. Let's say LED 1. We have two LEDs actually, by the way. So the one is the green one that you're already seeing. LED 1, and we let it flash red, and with an interval of 500 milliseconds. So let's see. Oh no, I was wrong. The green one is LED 2. So let me check my stream. Is this visible? Yeah, it's visible. That looks so. Basically, we are already at blinking light. So it's not a built-in blinking light, but we can, at least at the shell, we can actually do a blinking light, and we could also do like fun things here. For example, I just paste stuff from the example. We want some random things here. So that's so GRiSP LED pattern. Again, LED 1. I assume this is 100, and then basically we pass this fun. So So that's kind of like part of the API, that you can pass a fun that actually selects the color depending on whatever. So we do it randomly, but you could actually depend on read a sensor and have the light set depending on. So as you see, I hope you see, one of the LEDs like flash widely in all kinds of colors. So this is our RGB LEDs. And so how much time do we have? We have like 10 more minutes about. So one thing I wanted to show is how we actually add code here. So I already have the, oh, that's the supervisor. I need the application. Oh, it's GSOL control. Yeah, sorry. So that's the application where we only start the supervisor. We still want to start the supervisor because it's kind of like necessary. So, but we only assign it because we also need to return it, because that's what the app start function is supposed to do. So we need to keep the value. And we already want it running before we actually mess with the LED. And I copy this here from the serial thing from the console. Like we want this random function. Messed up. Oh, I have it twice now. Oh, that's the echo. Okay, don't need the echo. So we have the random function. Yeah, that's the Emacs indenting. Don't want this at the moment. And what we do is we also call the, basically call our function. And because it's funny, we also do this for the other LED. So we duplicate the function and also let it flicker randomly. And then we don't have to forget to return the supervisor. And let's see. So I shrink away the serial console again. So let's just compile and see if I made a typo. No, I didn't. Well, I was cut and pasting working code, so that was easy. Before we need to deploy, I actually need to take out the SD card. And put it in my Mac. Now we need some improvements for our stack. So the thing is now, because there's something on the SD card, I run this here to show you. It actually complains that the destination volumes GRiSP ini already exists, and you could actually use -- force to override. But I kind of like to have a clean slate and erase the previous contents of the SD card. So I could just run rm - rf volumes GRiSP, but what I could also do is I can add this to the rebar config to be done automatically. So this is basically, it goes into the deploy section. Oh, this is not in Erlang mode. So there's a pre-script, which is basically a shell command that is run before the deploy. And we want to rm - rf volumes GRiSP. Oops, this is normally uppercase. And not the actual directory, but we want to delete all the files on it and all the directories. So that's our pre-script. So it will actually be cleaned up before we do anything. And while we add it, we also add a postscript. as you might have imagined that exists also. Script, a postscript where we eject the disk. Disk util eject volumes GRiSP. So now it's pretty seamless. So we only have to plug in the SD card and then run deploy if I did everything correctly, and then we get a fresh SD card, copying release. So it's actually doing it. Render prescript, so you see running prescript. And something, oh, a typo, disk util. Disk util, there's a K missing. So we do this again. Ah, yeah, Adam posted where the documentation is actually. So I forgot to mention that the documentation for all these LED things is on Hexdocs. So, for example, that's the GRiSP LED thing. So there you get the whole API explained. Set it to a color. That's the thing that we did, flash. And the pattern was, the pattern can be a list or it can be a function, I think. Pattern, no time color. Actually, what did we do? I think the parsing a fun thing is not documented. Just a note. So because what we were using is pattern, maybe I misinterpreted. Time color, and color can be a color name or a color value. No, it's not documented. It can also be a fun, apparently. So yeah, the thing is it's already ejected, so I can just pull out my SD card, shove it into the still running GRiSP board, because if it doesn't write to the SD card, it doesn't care about. And let me set up settings. I need to make it a little bit shorter. Where's actually the size? Kind of can't shorten my serial thing. Don't know where I set this. Whatever. But that's annoying. Can I set the size of the window somehow? Somehow I can't resize. I used to be able to resize this, but somehow it broke. So maybe it's Twitch related. Something doesn't work. So what I do now is basically I just push the reset button. So there's a little button here. You can't probably see it well enough. And which resets the CPU. So I reset the CPU, and then you can actually, when you're already on the serial line, you can actually watch it boot. So here the bootloader tries to mount the SD card, mounted it successfully, and loaded the beam.bin file here. So that's here. And then lots of stuff is going on with Wi-Fi and all kinds of things. There are some error messages here which are coming out of libraries which we can't easily change. So usually one needs, it's kind of like unfortunate, like it would be that if there's no error messages, then everything is fine. So what we do here is starting Erlang runtime, but you can't see it anymore because my window is too large. So it says 8080 here, sorry. It says 80 times 80 here, and I can't change it. Hello, general. Paste and right click. Login, so that's not settings. Ah, screen size. Columns, rows, so you want less rows. 60? Yeah, now it fits. So now you can say actually also see the starting Erlang runtime. And as you see, it's kind of like we switched off logging because then it takes even more time. So there's a long pause while it actually starts. We are working on it. Let's say it like this. There's the thing is, this is a fat file system, and if you want to read lots of little files from a fat file system scattered all around, which is what the Erlang VM does at the beginning, this is not the most efficient way to use an SD card. We actually have a pretty efficient SD card driver, but it doesn't. It only can actually speed up if you read large blocks, and that's one of the things that one workaround against this. But now, as you can see, we already booted, and the shell is here, and our both LEDs are flashing randomly. So yeah, 0 to blinking light, managed to do it in the first Twitch stream. So expect real projects happening in the future weeks. So next time slot, next planned time slot is next Friday. So then we will actually look at the solar heating system and think about how we actually can control this and talk to temperature sensors and do things like this. Yeah, I hope this went well enough, so I don't have to delete the video afterwards because out of embarrassment. Thank you that you watched this, and hope to see you next Friday or in larger numbers even. So I think it's time to check out. So I have an offline screen. Okay, bye-bye. Have a nice Easter.